projects. In this video, we are going to explain about the project entitled as Digitization and Classification of Electrocardiograms for Automated Cardiovascular Disease Diagnosis using Machine Learning and Deep Learning Models. So before getting into the video, let me give you the brief description about the project. The project develops an automated system that digitizes ECG signals and uses machine learning and deep learning models to classify heart conditions. By converting raw ECG data into clean digital form and analyze it with intelligent algorithms, the system can detect abnormalities and assist in early diagnosis of cardiovascular disease. Coming to the abstract explains that ECGs are important tools for detecting heart diseases because they record the heart's electrical activity. However, analyzing ECGs manually can be slow and may lead to mistakes, especially when rely only on expert interpretation. To solve this problem, this project uses machine learning and deep learning methods to automatically digitize and classify ECG signals. The system first cleans and processes raw ECG data, then extract important features that represent the shape and timing of the heartbeats. Advanced models like CNNs, LSTMs, and hybrid networks are used to accurately identify different types of heart abnormalities. The main goal is to improve accuracy, speed, and reliability in diagnosing cardiovascular disease. The abstract also highlights that deep learning models perform much better than traditional methods, making the diagnosis process more precise and effective for clinical use. Coming to the existing system states that traditional ECG diagnosis mainly depends on manual interpretation by cardiologists who examine paper-based prints or digital waveforms displays to identify abnormalities. While these systems may include basic features such as simple filtering and rule-based detectors, they are limited in their ability to manage noisy signals, patient-to-patient variations, and complex arrhythmias. Most existing automated tools rely on handcrafted features and convolutional machine learning models like support vector machines and decision trees. These approaches require significant expert knowledge to design suitable features, and they often fail to generalize well when working with large, diverse datasets. Additionally, many of these systems do not support real-time classification and have difficulty integrating with modern healthcare platforms. As a result, their diagnostic accuracy and reliability remains relatively low, reducing confidence in automated ECG analysis. Coming to the proposed system or base paper work, the proposed system introduced a fully automated and intelligent pipeline for digitizing and classifying ECG signals using advanced machine learning and deep learning techniques. It starts by converting analog to scanned ECG records into high-quality digital signals. These signals then undergo comprehensive pre-processing steps such as a noise removal, segmentation of heartbeats, and normalization to ensure clean and consistent input data. Unlike traditional methods, this system uses deep learning models including CNNs, LSTMs, and hybrid CNN-LSTM networks that automatically learns meaningful patterns directly from the ECG waveforms without requiring handcrafted features. This allows the model to detect a wide range of cardiovascular abnormalities with high accuracy. The system also provides interpretable results to support clinics in making reliable decisions. Moreover, it is designed for flexible deployment on cloud platforms or edge devices, enabling real-time ECG monitoring, remote diagnosis, and seamless integration with electronic health record system. Overall, the proposed system enhances diagnostic speed, accuracy, and accessibility, ultimately improving clinical workflows and patient outcomes. Coming to the data set, for this project, we used the Mendeley ECG image dataset, which contains real ECG images collected from cardiac patients. These images include scanned or photographed ECG strips that have been digitalized, and organized specially for research on automated heart disease diagnosis. Because the data is in image format, it works very well with deep learning models, especially CNNs used for image classification. The dataset is available under a Creative Commons license, which means researchers can reuse and modify it as long as proper credit is given. However, it does have some limitations such as limited metadata and unclear class distribution. So additionally, pre-processing and manual inspection are needed. Even with these challenges, the dataset is widely used in academic and medical research projects, making it a reliable and suitable choice for training and evaluating our ECG classification system. Coming to the novelty or extension or enhancement or improvement. As an extension, we used several advanced 2D deep learning models such as VGG16, Exception, ResNet 50, NASNet Mobile, and an ensemble model combining Exception and ResNet 50. Among this, ResNet 50 and the ensemble model gave the best performance, achieving an impressive accuracy of 98.9% for ECG image classification. We also applied the YOLO family of models to detect abnormalities directly from ECG images, allowing real-time object detection. In addition to classification and detection, we used explainable AI techniques, especially GradCam, to generate heat maps. These heat maps visually highlights which region of the ECG image influence the model predictions, making the system more transparent and easier for clinicians to understand. Finally, we integrated all these components into a user-friendly interface using the Flask framework. This allows users to upload ECG images and receive predictions from the trained models, making the system practical and accessible for real-world usage. Coming to the flow of the work, firstly, we need to import the packages. The first module involves importing all the necessary libraries and packages required for the project. This includes tools for image processing such as OpenCV and Pillow, machine learning libraries like scikit-learn, deep learning frameworks such as TensorFlow Keras and PyTorch, and visualization libraries like Matplotlib and Seaborn. Additional packages required for YOLO model training and the Flask framework for deployment are also loaded here. This step ensures that the entire deployment environment is prepared with all the essential functionalities before starting the workflow. Next, dataset preparation. In the dataset preparation module, the ECG anomaly detection dataset is collected and organized for model development. For the classification branch, the dataset consists of ECG images labeled according to their classes, enabling the training of ML and DL classifiers. For the YOLO detection branch, bounding boxes annotations are provided in the YOLO.txt format, marking the specific regions containing abnormalities. The dataset is then systematically divided into training, validation, and testing sets to ensure effective learning, fine-tuning, and unbiased evaluation of the models. Next, visualization. This model focuses on understanding the dataset through visual analysis. A bar graph is generated to display the distribution of class labels, helping identify class imbalance. Sample labeled images and YOLO annotated images are also visualized to verify the accuracy of annotations and ensure the dataset is correctly structured. Visualization plays a crucial role in the identifying potential issues early and gaining insights into dataset quality before pre-processing and model training. Next, we have pre-processing. The pre-processing module prepares the ECG images for model training. For the classification branch, images are resized to a uniform size, converted to floating point format, normalized, and then transformed into NumPy arrays. Scaling techniques are applied and PCA is used to extract important dimensionality reduced features. Transfer learning models are also employed to extract deep features for classical ML algorithms. For the YOLO branch, A data.yaml file is created containing images path and class names. And the dataset is arranged into two parallel pipelines, one for the classification and other for detection. This ensures each model receives data in its required format. And next, we have model training. The model training module involves two major branches. In the classification branch, traditional ML models such as KNN logistic regression, SVM, XGBoost, and voting ensemble are trained alongside deep learning models like ResNet 1D and EfficientNet 1D. The extension includes several powerful 2D CNN architectures such as VGG16, Exception, ResNet 50, NASNet Mobile, and an ensemble model combining Exception and ResNet 50, which significantly improves classification accuracy. In the YOLO branch, different YOLO versions including YOLO V5, YOLO V8, YOLO V9, and YOLO V11 are used to detect abnormalities with ECG images. These models learn both the location and class of abnormalities through bounding box prediction. Next, we have evaluation. In this module, the performance of the trained model is evaluated using various metrics. For classification model, metrics such as accuracy, precision, recall, F1 score, confusion matrix, and ROC AUC curve provide a comprehensive understanding of model behavior. For YOLO detection models, performance is measured using MAP, mean average precision, and recall to access how accurately the model detects and localize abnormalities. Different YOLO versions are then compared to identify the best performing detection model. Next, we have interface pipeline. The interface pipeline describes how the system works during real-time usage. When the user provides an ECG image as input, the YOLO model first detects and marks abnormal regions on the image using bounding boxes. Next, the classification ensemble predicts the type or class of ECG abnormality. The final output includes the processed image with bounding boxes. The predicted class label and the confidence score enables clear and interpretable results for users or clinicians. And next we have Flask web app. The final module involves deploying the trained models using a Flask-based web application. The front end consists of a simple HTML interface where users can upload ECG images. The backend integrates the YOLO detection model and the classification ensemble to process the input image and generate predictions. The application then displays the output, including the detected bounding boxes, predicted abnormality type, and confidence score. This module provides a user-friendly system that applies the trained models in real-world scenarios, making the project accessible and practical. The algorithms used are, for classification, we have trained ML and DL models like KNN, logistic regression, SVM, XGBoost, voting ensemble, ResNet 1D, EfficientNet 1D. And extension models, for 2D models, we have used BGG16, Exception, ResNet 50, NASNet Mobile, and Ensemble, which combines Exception and ResNet 50. And the extension YOLO-based classification, we train ECG detection using YOLO V5, YOLO V8, YOLO V9, and YOLO V11. Coming to the requirements, we have hardware requirements and software requirements. Hardware requirements consist of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap. To execute the project first, we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations, such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. These are the notebook.ipynb files. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the project execution, copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. Using the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number 5000. Copy the link provided by the framework and paste it into any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front-end built using Flask framework. In this page, we have home button and sign up button. Now click on sign up button so that the logon HTML page will be opened. Here, we need to give the details and create an account for user authentication like username, full name, email ID, mobile number, and a strong password. Then click on create an account so that all the given details are stored in signup.db and then the login HTML will be opened where you need to access the application by username and password. Then click on login so that the prediction page has been displayed. In this page, we have prediction button, graphs button, notebook button and sign out button. Firstly, click on prediction button. As we are doing both classification and detection, first we will test the classification so that the ECG cardiovascular disease classification will be opened where you need to upload the ECG image and classify. Here, we need to upload the image from the code folder. In this, we have test cases. Click on classification and open any one of the folder and select an image, then upload the image. The ECG report has been applied. Now, click on classify ECG image. The input will be pre-processed and the output will be displayed as the classification results are arrhythmia. The confidence level is 98.57%. The original ECG image is given here and the GradCam heat map image is given here. And we also have the causes of arrhythmia and precautions of arrhythmia. Then click on upload another image so that we can give an other image for classification. So the image is given and we need to click on classify ECG image so that the input will be pre-processed and output classification results are like MI. The confidence level is 99.82. The original image is given here and the GradCam heat map image is given here. MI is known as myocardial infarction. It is a heart attack. The causes are given and the precautions are given. And then come back and click on detection so that the ECG YOLO pattern detection will be opened. Here we need to upload the ECG image. This also we need to upload from the test cases which are present in the code folder. Detection, select any image and click on open so that the image will be uploaded. Then click on detect ECG patterns. The input will be pre-processed and the output will be displayed as The YOLO detection results are given here. Like it is detected as ECG pattern detection. The detected ECG patterns using bounding box are being shown below. The given image is having arrhythmia. And we also have the detection capabilities and the detection benefits. In the same way, we can upload the other image and check the YOLO detection. Now, click on View Analysis Graphs so that the classification data visualization graphs and the YOLO detection data visualization graphs will be displayed. Firstly, let us check with classification data visualization graphs. First, we have number of image count per class graph. This bar chart displays the number of images available in each class of data set, highlighting how the samples are distributed. Among the four categories, the normal class contains the higher number of images, indicating it is the most represented group. The MI and arrhythmia classes follows closely with 239 and 233 images respectively, showing relatively similar representation. In contrast, the PM class has the fewest images at 172, making it the least represented category. Overall, the graph shows a moderate imbalance across classes, which may influence model training and should be considered during data pre-processing or model evaluation. Next, we have confusion matrix and ROC curve. The two graphs together illustrate the strong performance of the hybrid ensemble model. The confusion matrix on the left shows that the model correctly identifies almost all samples in each classes, with only one or two misclasses occurring overall. Arrhythmia, MI, normal, and PM images are classified with very high accuracy, and the MI and normal classes in particular are predicted perfectly with no errors. On the right, we have ROC curve further confirms the model's outstanding performance. All four classes have the AUC values of 1.00%, indicating perfect discrimination capability between each category. The curves for all classes rise sharply to the top left corner, which represents ideal classification behavior. Together, the results demonstrate that the hybrid ensemble model is extremely effective and reliable for distinguish between arrhythmia, MI, normal, and PM ECG images. And next we have accuracy by model graph. The bar chart compares the classification accuracy achieved by different machine learning and deep learning models. Overall, it shows the most models perform very well, with several reaching near perfect accuracy. Among the best performance are ResNet 50, Hybrid Ensemble, Voting Ensemble, Logistic Regression, XGBoost, SVM, and KNN, all of which achieve accuracy closer to or at 100%, indicating strong reliability in identifying the correct classes. Models like ResNet 1D, Exception, and EfficientNet 1D also performs well, but with slightly low scores. In contrast, VGG16 and especially NASNet Mobile shows noticeably lower accuracy, suggesting they are less effective for this particular task. Overall, the graph highlights that ensemble methods and certain deep learning architectures deliver the highest performance while a few models struggles in comparison. Next, we have F1 score by model graph. This graph illustrates that the F1 scores of different machine learning and deep learning models, showing how well each model balances precision and recall. Most models, including KNN, logistic regression, SVM, XGBoost, voting ensemble, ResNet 1D, exception, and ResNet 50, achieves very high F1 scores close to 1.0%, indicating strong and reliable performance. The hybrid ensemble model stands out with the highest score, demonstrating its superior ability to produce consistent and accurate prediction. EfficientNet 1D performs moderately well, but slightly below the top models, while VGG16 and especially NASNet Mobile shows significantly lower F1 scores, reflecting weaker classification performance. Overall, the graph highlights that ensemble methods and certain deep learning architectures perform expectationally well, whereas some models like VGG16 and NASNet Mobile struggles to achieve balanced accuracy. And next, we have recall by model graph. The graph shows the recall scores of various machine learning models, highlighting how efficiently each model identifies positive cases. Most models achieve very high recall, close to or above 0.95%, including KNN, logistic regression, SVM, XGBoost, voting ensemble, ResNet 1D, exception, ResNet 50, and the hybrid ensemble, with the hybrid ensemble attempting the highest recall at roughly 0.99%. EfficientNet 1D performs slightly lower, around 0.78%, while VGG16 and NASNet Mobile shows noticeably weaker recall at approximate 0.57% and 0.39% respectively. Overall, the comparison illustrates that traditional ML models and several deep learning architectures excel in recall, while a few specific CNN architectures lag behind. Next, we have precision by model. This graph illustrates the precision scores achieved by a range of machine learning models, showing how accurately each model identifies true positive predictions while avoiding false positives. Most of the models, including KNN, logistic regression, SVM, XGBoost, voting ensemble, ResNet 1D, exception, ResNet 50, and the hybrid ensemble, achieve very high precision values, close to or above 0.97%, with the hybrid ensemble reaching perfect precision at 1.0%. EfficientNet 1D performs moderately well with a precision of about 0.82%, while VGG16 and NASNet Mobile shows significantly lower precision at approximate 0.60% and 0.35% respectively. Overall, the results indicate that the majority of traditional and advanced deep learning models produce highly accurate positive predictions, whereas a few specific architectures struggles with a higher rate of false positive. And next we have YOLO detection data visualization graphs. In that, first we have YOLO precision score graph. This graph compares the precision performance of 4 YOLO models versions like YOLO V5, YOLO V8, YOLO V9 and YOLO V11, highlighting how accurately each model identifies true positive detections while minimizing false positives. Among the models, YOLO V8 achieves the highest precision, reaching close to 0.97%, indicating very accurate predictions. YOLO V9 and YOLO V5 perform moderately, with precision scores around 0.74% and 0.72% respectively, showing reasonable but less consistent accuracy compared to YOLO V8. YOLO V11 records the lowest precision at approximately 0.63%, suggesting a higher rate of false positive. Overall, the graph demonstrates that YOLO V8 provides the most reliable detection accuracy, while the newer YOLO V11 version underperforms relative to the others. Next, we have YOLO recall score graph. The chart compares the recall performance of 4 YOLO model versions V5, V8, V9 and V11. Recall measures how well a model correctly identifies all relevant objects, so higher values indicates fewer missed detections. In the graph, YOLO V5 and V8 shows the strongest performance, both achieving recall scores close to 0.95%, meaning they successfully detect nearly all target objects. YOLO V9 follows with a slightly lower recall, just above 0.9%, still indicating solid detection capability, but with a smaller increase in missed objects. YOLO V11, however, shows a noticeable drop to around 0.68%, suggesting that this version misses significantly more relevant objects compared to the others. Overall, the visualization highlights that the older YOLO versions outperform V11 in recall for this dataset or task. And finally, we have YOLO MAP score graph. This graph illustrates the mean average precision performance of 4 different YOLO model versions: V5, V8, V9 and V11. MAP is a key metric that measures how accurately a model can both detect and correctly classify objects, making it a strong indicator of overall detection quality. In the graph, YOLO V8 achieves the highest MAP, close to 0.98%, showing superior precision and overall detection reliability. YOLO V5 and YOLO V9 follows with similar performance level, both around 0.88% to 0.90% range, indicating they also deliver strong detection accuracy but slightly below V8. In contrast, YOLO V11 shows a significant drop with MAP around 0.55%, meaning its predictions are noticeably less accurate and consistent compared to the earlier versions. Overall, the chart highlights YOLO V8 as the best performing model in terms of MAP, while YOLO V11 performs considerably worse in this metrics. Then click on Sign Out. So finally, in this project, a complete automated system for ECG classification and abnormality detection was developed using machine learning, deep learning and YOLO-based models. The system successfully digitalized and analyzed ECG images, achieving high accuracy through advanced models such as Resonance 50, Exception and Ensemble architectures, along with multiple YOLO versions for precise abnormality localization. The integration of GradCam improves transparency by highlighting important regions influencing predictions, while the Flask-based web application provides a user-friendly interaction for real-time interface. Overall, the proposed approach enhances diagnostic accuracy, reliability, and accessibility, demonstrating strong potential for clinical applications and supporting faster, more efficient cardiovascular disease diagnosis. This is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.